This meeting is now being recorded.
Good morning, everyone. This is Diego Davis. I'll be your speaker today from Xylem Inc. We'll just hold on a couple more seconds here.
Okay. It is time to start now. Good afternoon, ladies and gentlemen. Welcome to the Office of Information Management and Analysis Brown Bag Series. The webinar will be strictly 30 minutes event for both presentation and questions and answers. So the title of today's webinar is Continuous Flow Monitoring, Latest Tools and Techniques Using Acoustic Doppler Instruments. The presenter is Diego Davis. Diego is the Regional Technical Sales and Support Manager for Xylem. He received his Bachelor of Science degree in Environmental Systems, Earth Science from the University of California, San Diego in 2011. In his former role as a hydrologic technician, Diego managed and executed projects over a wide range of applications, such as measuring piped and open channel irrigation flow, stream gauging per USGS protocol, monitoring meteorological conditions, real-time data telemetry, and beta testing. In his current role, he provides technical and consultative support for YSI SoundTech and waterlogged products lines to agencies throughout California, Arizona, Nevada, and Hawaii. With this brief introduction, I'll pass the phone line to Diego to present. Okay, can go ahead and start presentation, Diego.
Okay, thank you very much, Dawit. And just want to make sure you guys can hear me on that side.
Yes. Yes. Yes.
Sounds great. Okay, well, let's just go ahead and jump into it. I want to first and foremost thank the water boards for hosting this brown bag session. Like Dawit had mentioned earlier, today's topic is going to be continuous flow monitoring, the latest tools and techniques using acoustic Doppler instruments. And so, like he had mentioned, I am the technical sales and support manager for Xylem Incorporated. I cover the YSI, SoundTech, and Waterlog brands. And today we're going to focus specifically on SoundTech and continuous flow monitoring. So to jump right into it, these are the three classic configurations of acoustic Doppler instruments, specifically continuous acoustic Doppler instruments. And I want to go ahead and just, really explain the illustrations that we have here and how all these kind of work. So if we take a look at these three different arrangements here, all these different types of technologies use the same actual sensing element. So they use what we call a transducer, and we'll get a little bit further into that. So it's the same technology, and all that's really happening here is that we are changing the configuration of how we physically align those transducers and measure water velocity and water level. On the top left, we have what we call an uplooking system. An uplooker, what it does is it profiles velocity with a front-facing beam, a back-facing beam, and then two skew beams. Additionally, it's going to measure water level with this vertical beam here in the center, and also an internal pressure transducer. Now, when you combine mean velocity that's measured by the instrument, water level measured by the instrument, and a user input channel geometry, the instrument can automatically calculate flow and as well as total light volume. So if you kind of take those same, that same principle there and apply it to everything else that's going on here, hopefully it's simple to understand that the IQ pipe, this is a different piece of instrumentation here, is doing the exact same thing. We're measuring water velocity as it moves down the pipe over the sensor. We're measuring water level. We're putting in the user input geometry, which in this case is a round pipe, could be an irregular pipe, an oval shaped pipe. All those can be accommodated in the geometry configuration. and then we are calculating the discharge, calculating the flow that's moving across. If we take a look at this bottom figure here, this is what we call one of our side lookers, and this is also pretty standard amongst all the acoustic Doppler manufacturers out there. The side looker essentially has one beam that looks upstream, and so it profiles velocity upstream, and then another beam that profiles velocity downstream. Again, we're measuring water level here, and we are also using the internal pressure transducer as well as the vertical beam for redundant level measurement. And with a user input geometry, we're able to calculate flow and save those data continuously to build a nice record here for either flow studies, investigative studies, billing, looking for any sort of events. That's all kind of the data that's produced from those instruments. And so one of the main pieces of theory I want to cover here today and not get too crazy into it is the Doppler shift. Now, the Doppler shift is really the founding, it is the main principle that we use in order to measure water velocity. Now, there's one key assumption to what we do here with our acoustic Doppler transducers, and that is that what we're measuring here is actually the velocity and the direction of particles in the water. And these particles are typically, silt, any sort of turbidity. These are just small particulate in the water that reflect our signal and in turn allow us to calculate the position, the direction, and the velocity of that particular particle. Now, you guys, I imagine you all can imagine that the more particulate we have in the water, the better scattering conditions we're going to have, the higher number of objects we're going to be able to measure, and the better and the more accurate our velocity measurement. So one really key part of this is that water with very low scatter, so this is water that's very, very clear, typically water that is fresh spring water, any sort of kind of treated water before it receives any sort of minerals or additives. This is going to be water that's very difficult to measure because there are very few objects in it that we can use to measure the water velocity. And so what happens in a Doppler shift is essentially we send out a small frequency of sound, and it reflects off these particles, and we wait to listen for that. And when we wait to listen, what we end up getting is we're able to measure a Doppler shift. So just as you guys are seeing here, that object is going to show that it's biasing in a certain direction, and that direction and velocity can be measured and then calculated into a mean velocity for that particular transducer. So just to kind of give you something familiar, something that you may be familiar with, a fish finder is a classic example of an acoustic Doppler transducer. And so what is a transducer and what does it do? Simply put, it sends a signal that will bounce off an object and will also receive the signal. And so in a fish finder, as many of you are familiar with, all we're really looking for is essentially this perpendicular path here to an object, because all we're really measuring is the time that it takes for the signal to reach an object and come back. And then based on that time and then water temperature, we're able to determine what the sound speed is and then what the distance is to that object. Now, with our acoustic Doppler transducers, one thing that we do is we actually shift the angular rotation of our instrument, and that incidence angle allows us to measure velocity and direction as opposed to just distance. Now, the last part of the transducer, and one of the key parts of what makes it so great, is the ability to profile velocity. Many of you may be familiar with the classic mechanical current meter. The way that this works is that as water moves past these spinning cups, one rotation equals a certain amount of water distance, and an operator will typically count the number of clicks over a specific time, and then also be able to calculate mean velocity using number of rotations and also elapsed time. Now, that's good if it was like 100 years ago, but since then we've come up with some great electronics that really make all the moving pieces of a mechanical current meter as well as the data processing a lot more streamlined. Now, I'm not knocking on mechanical meters. This is a very tried and tested and proven technology, and it's still used to these days. It's just a little old. And so as we move over to something like an ADCP over here on the left, what we see here with an ADCP is that from one unit, this one has two transducers here, we're able to profile velocity, and we can actually separate these different profiles and bin our velocity so that if we want to, focus in on a certain section of the cross section a little bit further, we can do that. So this essentially, from one unit, we're able to do what would take a number of mechanical meters to do. I also want to kind of discuss the operation of the different configurations we discussed. So for an uplooker, what we're really looking to do with our velocities and our beams here is profile velocity. We're trying to get a good understanding of what the velocity flow field looks like as it passes over the channel to get a really accurate mean velocity. In the past, we used to just use the center beams, so the along axis upstream and downstream beams to measure mean velocity. However, these flow conditions the calculation that we use is theoretical, and if we're not able to measure the edges, the theoretical calculation doesn't hold up for every site. And so the addition of skew beams really allows us to kind of get into the portion of the channel that's not being directly measured and actually get a direct measurement to complete the flow field and understand, the flow dynamics at that particular site. We talked a little bit about the IQ pipe, and if we take a look, this is another uplooking instrument. And just kind of go back one more slide, we can compare the geometry of this instrument with the IQ. And you can see in the IQ pipe that it's a lot narrower, and we did that specifically to optimize the beam paths in a round pipe or in a closed conduit situation. Obviously, we're going to want to bring those beams in a little narrower, and that will be a lot more representative of the actual pipe that we're measuring, the center line as well as the skew velocities off that transducer. The last piece and the last configuration we'll talk about is our slide looker. The slide looker has some great advantages, including the ability to access it very easily. So this is typically mounted off, a sidewall or maybe up here or a pylon or something that makes it easy to pull up or access, and that is a big advantage of it. The way that this operates is similar to all the other pieces. There are two beams, one looking upstream, one looking downstream, a vertical beam, as well as an internal pressure transducer, which will redundantly measure water level. And then based on a user input geometry, flow is calculated and logged on a user-based interval. So some important things I want to talk about, field installation guidelines. So number one consideration is location. It is the most important part of your data collection, your installation, your maintenance of the site, and the longevity of that site. One of the things that we're always going to be looking for is a long, straight section of uniform shape, but especially in natural flow conditions, that can be difficult to find, and it really becomes a situation where you just work with the best option that you have. So you'll have my contact information at the end. Always feel free to give me a call and consult and say, hey, this is a good site, this is a bad site, what can be, how can it be improved, and so and I'll be glad to consult you on that. Some things you're really going to want to avoid include changes in the channel shape. You don't want to be next to any sort of inlets and outlets. And then for the IQ, the uplooking models, soft channel beds with high sediment transport are going to be an issue, obviously, because that instrument can become buried. And once it becomes buried, it'll be difficult to get data off it until you're able to wipe it down or maintain it. For side-looking instruments, the big consideration is going to be vegetation and beam obstruction. So if we are looking out into the channel, but then we have a wall of, let's say, algae growing up, and it interferes with the beam path across the whole channel, then we're only going to be measuring the distance between the sensor and the nearest obstruction. So it's important to have a cross-section that's free of debris, vegetation, obstructions, and that's going to be very key for the side looking. Mounting is also very important, especially with the up-looking options. You're always going to want to mount an instrument level and align it with the x-axis down the middle of the channel. With our side-looking instruments, depth is going to be a major consideration. So you want to install the sensor, near the minimum expected water level. But ideally, this instrument is going to be located at about 50% of the water columns. So it doesn't really do well with really quick water level change. The IQ would be more suited for that. But if you have a channel, let's say a river that doesn't really change too much in water level, the SL is going to be a great option there. Another important consideration is mounting and routing your cable through a conduit for protection. This is a really common issue, is not routing your cables through conduit. It's going to leave it susceptible to any sort of vandalization, vandalizing, any sort of animals, any sort of debris coming down that might nick the wires. These are all risks that you run when you don't route that cable through a conduit. And then the last one is channel dimensions and survey. This is also a very important part of the flow calculation, so it's important to get it very accurate. Sometimes engineering drawings don't quite cut it. It's not the as-built, so it's really important to actually get in there and measure it somehow. Site selection, like we talked about, just wanted to give you all a couple examples. Everything up top, these would not be recommended sites. So as you can see, the site over here on the left, this site is 3 pipes that are all converging together, and it really makes for a nasty and turbulent situation of trying to measure velocity. In the middle, we see high meandering in this channel here, which might work at lower flows, but as you all can imagine, at higher flows, this is going to be a very difficult site to measure with a lot of turbulence. And lastly, over there on the top right, we see an IQ pipe that hasn't necessarily been pushed back far enough into the pipe. And so we have this weird flow dynamic going on where, we have this big basin spilling into this pipe, and it's going to create a turbulent condition that isn't very uniform. On the bottom here, we kind of see examples of very good sites. So we see someone taking a weighting discharge measurement in a nice straight section of canal. In the middle, we also see a nice, long, straight, uniform section of canal, a very uniform flow there. And then the last one, we see an IQ pipe installation. This is pretty common for what those installs look like. Just kind of want to reiterate some of the important components of site selection, which we're going to include, to try to avoid multiple channels. Make sure that it's safe to measure, or as safe as possible throughout all the seasons. And stability. Don't put this instrument in soft sand and expect it to beat back, after a high storm. If you have soft banks and things like that, these are all kind of safety precautions and installation considerations that you'll want to make while selecting a site. We put this beaver down here because the beavers love to chew the cable, so make sure you route those cables through conduits. Side looking versus up looking. I want to cover here some of the advantages and when to use one over the other. We'll start with the side looking option up top. The advantage here is that it's easy to access. If you're installing this off a sidewall, it's easy to install a sliding rail system, which are typically provided with these instruments, and really access it easily. If you have any issues, if you need to wipe it down, you just need to check on it. If you need to change the height, this is going to be a really great option. The disadvantage, like I said and mentioned before, is that it doesn't handle water level very well, very fast water level changes. So it's important to kind of plan for very steady water level. On the other side of things, the up-looking option has its advantages in that it does handle water level change very well. and some of the disadvantages are going to be that you have limited access, especially if the channel's full, and then you have the possibility of burial as well. I kind of just brought this slide up to just show what a good, clean site would look like. Here's the instrument routed through a small conduit, and then the conduit feeds right up into an enclosure here with a data logger and solar panel and whatnot. I'm just kind of reiterating a couple of installation considerations, but one of the things that we also offer here is a beam check. A lot of the manufacturers include this, and what it really does is just allows you, if we take a look over here, to see where the reflections are happening and see if there are any sort of interferences with your beam paths. Some other typical maintenance that you're going to want to, conduct with these instruments include inspecting the cables, especially if they're not in conduits, making sure that, they're not bent or nicked or, that nothing nasty has happened to those cables. And then you'll want to wipe down the transducer faces, especially in places where you see a lot of high biofouling. This is really going to improve the condition of your measurement. I want to talk about instantaneous discharge measurement briefly. Instantaneous discharge measurement is the means to validating your continuous data. Oftentimes we set a sensor in there, we program everything in there, and the way to verify that number is actually correct and accurate is to use a secondary instrument. This is essentially the approach to that, where we take an instrument that's going to be measuring width, depth, and velocity throughout the column, and we use all of those just like we would in our flow calculation continuous instruments to calculate a discharge, a mean area, a mean velocity, all parameters that can be matched up or compared with your continuous instruments. So two ways that we do that. The first would be a weighting discharge measurement. The flow tracker is a very standard piece of how that's done. And essentially what we're doing in the flow tracker is just measuring a point velocity at each one of these locations along the channel, entering the depth, and then as we move across, entering the width. At the end, the flow tracker will calculate all the values for us and give us all the statistics on the data that was collected there. If a weighting discharge is definitely not possible, maybe you have a higher water situation or you're in a very deep channel, an acoustic Doppler current profiler is going to be the next best option. And this is essentially a floating platform that you can drag from one end, from one bank to another, and it profiles. It essentially does what the flow tracker does, except on a very, very detailed scale across the whole channel there. As you can see, there are several different ways to approach this. So you can either use a tag line like we have here on the bottom left, or you can mount it to a boat like we have here on the right. Lastly, I just kind of want to cover the last component, and that's monitoring. So remote monitoring is a very important part of what's going on today. And I'm just going to show you a simple suite that we have here. That kind of illustrates what kind of the advantages here of monitoring. And so if we go to just kind of a home screen, and this is one of our users, you can see that they have several sites here, and they're actually color coded by what the water flow is looking at. So looking like. So you have a really nice bird's eye view of all the different kind of conditions that may be going on. You can set alarms, you can set email notifications, and then you can also just view directly what's happening at that site. What was my last measurement? And we can see here, all right, that looks good. Last measurement looks okay. And we can go ahead and zoom in and take a further look at some of the data here. What does the gauge height look like over the specific period? Maybe I want to change my parameters here and just look at water temperature or connectivity. And then from this interface, you have the ability to download data as well. So I'm going to wrap it up and leave some time here for questions. And if you all have, give me a second here. Yeah. If you all have any specific questions, then go ahead, and I think we're going to be opening that up to everyone now.
Yeah. So we can ask questions now. It is open for questions.
All guests have been unmuted.
Yeah, all guests are unmuted, so people can ask from the phone too. questions for chat?
Right. Right.
Okay, go ahead.
Do we have access to the remote data that he was mentioning, the remote monitoring data?
You mean here, or are you asking here?
Here.
No.
We don't have access to it.
No. Okay, is there any questions, or is that...
Well, so we're having a discussion here at Region 1. There was, we were just looking at the first bottom-up model that all the example conditions were kind of man-made structures, really required a straight shot channel. And is that like it seemed to be provide a fundamental limitation to in-stream uses. Not that it couldn't be used in that scenario, but we have to find a very straight and kind of limited condition channel configuration. Is that correct, or can you elaborate on its applicability in in-stream uses?
Sure, yeah. And so I think you bring up a good point. You know, how common is it that we go out into the field and we find this nice straight, you know, geometrically even cross-section, and that's very rare. It's a unicorn out there. And so there are really two approaches to it. The first one is, especially with earthen channels, the banks change really quick. So one big episode comes through and your entire cross-section is completely different. Your flow calculation is completely different. And that can make it a little bit difficult. And so for calculating consistent flow. So there are two approaches here. Either you find a way to, reshape the channel, which is going to be rare. There's also the ability to match up your instantaneous discharge measurements with simple parameters such as water level. So what you'll often see with a lot of USGS string gauging is that all they measure is water level, but they'll go out and create a relationship with their instantaneous discharge measurements to create that kind of continuous recorded data and still include the flow calculations for each sample point. So, yeah, it's going to be really difficult to find some sites out there, especially in natural channels. I would say that some of these products are really targeted for maybe smaller studies, 1 week, 2 weeks, where you can kind of predict how much rainfall and water you expect to come down. And if it really gets to a nasty situation or it's just impossible to find a site, possibly the next best option is going to be to use instantaneous discharge measurements and create a rating curve with a water level. Yeah.
Thank you.
I have a question. You show on one of the slides about either putting it on the side of the channel or at the bottom of the channel. And each has different advantages and disadvantages. Have you tried maybe where you can put both on the side and on the bottom, and then kind of, is there a way to merge the information to get a complete picture of the flow and water level and everything?
So that's actually a good idea. We have a couple test sites, where we have one channel, but we'll put several different pieces of instrumentation in there just to do, comparative studies. So we'll put an uplooker, a side looker, and then we'll simultaneously do a flow tracker measurement. And so all that data definitely can get produced and used. I guess the caution I have here is that we wouldn't be able to combine the two different sensors to produce a calculated flow number. That would probably have to be done like through a data logger or something that had the means to take all the different parameters and then calculate a value that could be stored as well, sample by sample. So short answer to your question is it wouldn't produce a direct discharge or a flow number, but all that data could certainly be loaded into a data logger, something like a Campbell Scientific data logger or Waterlog or Citron data logger, and used to calculate that flow value, yes.
Thanks.
You're welcome.
Okay, if there is no any other question, it is time to close. We will post his presentation on our website. That information is available in the slide. So thank you all for participating. Thank you, Diego.
Thank you, Dawit. Thank you, everyone, for joining.
All right, bye.
Thanks.
The host has left the meeting. So at this time, the meeting will come to an end.